Hi all, we are going to discuss about photochemistry. Photochemistry is the branch of chemistry concerned with the chemical effect of light, that is far UV and IR along with visible light. And photochemistry deals with the interaction of radiation or light or the electromagnetic radiation with matter that brings out a photochemical change or a photophysical change. That's how it has to be told. We are supposed to go through many of the organic reaction as far as organic compounds are concerned. The photochemistry is very important. You could see a typical reaction over here. I have taken cis cyclobutene and it is going for ring opening. Concerted ring opening means the making of the bond and the breaking of the bond all happen simultaneously. That's how it is told, concerted reaction. And here opening of cyclobutene is happening into butadiene and you are getting two different products. If you keenly observe on the reaction arrow mark, you could see that one side it is H nu, it represents the absorption of radiations and you get a product which is stereo specific. You could see 2E, EE configuration. Whereas if you heat cis cyclobutene, you are going to get a product with Z configuration. So the ground state and excited states have different electronic structure and orbital symmetry. That's why it is leading to form different chemical properties. Photochemistry in everyday life, it's very important. It's in the nature, it's in the medicine, it's in the industry. In the nature, the ultimate source of energy for all the living beings on the earth comes from the sun and it is made accessible to the all living organism by photosynthesis. We see things. Our vision is connected to photochemistry. Phototropism, that means if you plant a small plant, that will be, its branches will be growing towards wherever sunlight is available. That's what we call phototropism. The ozone layer, ozone depletion, ozone formation. For treatment of jaundice of newborn babies, we use photons. Photodynamic therapy, it's nothing but photochemistry. In industry, for photography, for photopolymerization and degradation of polymers, photocopying and photochromism, which we use in sunglasses as the examples of the substances which comes under the photochemistry. Photochemistry means it is the chemistry of light. So what sort of light are concerned with the photochemistry? If you ask, you could see the broad electromagnetic spectrum over here. Visible light, of course, along with far infrared light and ultraviolet light is what could contribute to photochemistry. Photochemical reactions involve electronic excited states formed by absorption of light, that is near UV, visible and near IR. Photochemistry versus photophysics. When you are going to deal with the photochemical process, there are two terms you must understand. One is photochemistry, the other one is photophysics. The definition is based on the stability of the products. A photochemical reaction leads to the chemical species. When I say leads to the chemical species. That means a stable species is formed. A photophysics comprises, there in the photochemical reaction you could expect a chemical change. Photophysics comprises those processes leading to the deactivation of electronic excited state to the initial ground state. It is a matter of excitation and de-excitation. That process is called photophysics. And we are supposed to learn 4 laws in photochemistry. 2 laws about the absorption of light and 2 laws about the primary process. That's going to we are going to learn soon. We are discussing about the laws that is concerned about the absorption of light. The first one is Lambert's law. This law states that the decrease in the intensity of monochromatic light with the thickness of the absorption medium is proportional to the intensity of light. That means when you are going to conduct any experiment related to the photochemistry, there the absorption of light happens. Generally we take the substance in a solution and we send the radiation. This law states that the decrease in intensity of monochromatic light, in order to avoid the confusion, we have taken a light which is having the identical frequency, so we call it as monochromatic light with the thickness of the absorbing medium. So this container is the absorption medium and the thickness is the thickness of this absorbing medium is proportional to the intensity of incident light. So the decreasing intensity of light with the thickness that is made constant is directly proportional to the intensity of incident light, and it could be written mathematically as minus di by dx is directly proportional to intensity of incident light. And when you remove the proportionality, you can write it as minus di by dx is equal to ki. K is the proportionality constant, which on integration changes to, you can even write like this: I is equal to I naught e raised to minus kx. I naught is the intensity of incident light, I is the intensity of transmitted light, and k is the absorption coefficient. So this is what about the first law, that is what we call Lambert's law. And the second law is what we call Beer's law. It states that before it was mentioned about the decrease in intensity of the light is directly proportional to the incident light. Here we are going little more ahead. It states that the decrease in the intensity of the monochromatic light with the thickness of the solution. Before it was told the intensity of incident radiation, but now it's not only proportional to the intensity of the incident light but also to the concentration of the solution. So it says that if you take a solution having high concentration and if you take a solution having low concentration, of course the one which has high concentration will absorb more radiation, so the intensity of the radiation which is going through the solution having more concentration will be decreased more. That's what. So mathematically it could be represented like this: di by dx is directly proportional to IC. It could be represented as di by dx, decrease in the intensity with respect to the thickness, is directly proportional to IC. And when you introduce a constant, you can write epsilon IC, which on integration gives like this, that is I naught, I is equal to I naught into e raised to minus epsilon IC, where Epsilon is the molar absorption coefficient, or it could be called as molar extinction coefficient. And once the absorption happened, so we have already learned two laws. One is Lambert's law, the other one is Beer law. One molecule is, if they ask Beer-Lambert's law, you can write the last law, that is Beer law, that will do the needful. Primary process. A molecule is excited into an electronically excited state by absorption of a photon. It can undergo a number of different primary processes. So these are the basic you must know. One is photochemical. The processes are those in which the excited species dissociates, isomerizes, rearranges or react with another molecule, and it will give a product which is stable. A photophysical process includes the radiative transition, in which the excited molecule emits light in the form of fluorescence or phosphorescence and return to the ground state. The intramolecular non-radiative transition, in which some or all energy of absorbed photon is ultimately converted to the heat. So here the molecules are getting excited and they are emitting the absorbed energy in the form of radiations. Or it could be like a molecule is absorbed energy, that energy is transferred to another molecule by colliding with that molecule. So the energy will be transformed in the form of heat. So once the absorption happened, how the photon will interact with the molecule, that's what next law is talking about. One of the law is Grothus-Draper law. Grothus-Draper law states that only the light which is absorbed by a molecule can effective in producing photochemical changes in the molecule. Means, if light is absorbed, then only you can think about photochemical reaction. Stark-Einstein's law, quantified law, it states that for each photon of light absorbed by a chemical system, only one molecule is activated for a photochemical reaction. The energy absorbed by 1 mole of reacting molecule is given by E is equal to NH nu. Means, if one photon is absorbed, one molecule will be activated. So 1:1 ratio. This energy that is observed by 1 Avogadro number, or 1 Avogadro number of molecule, or 1 mole of reacting molecule, is given by E is equal to NH nu. That energy possessed by 1 mole of photon is what we call 1 Einstein, that is 11.97 into 10 raised to minus 5 per wavelength kilojoules per mole. Photochemical rate law, that is again called as Einstein's equivalency principle. That means one particle of a chemical substance can absorb only one photon from light beam. That is given as delta E is equal to H nu. So for 1 mole it is delta E is equal to NH nu. So Einstein's equivalency principle or photochemical rate law means one particle of a chemical substance can absorb only one photon from the light beam. That is delta E of that light beam is equal to H nu. So here Stark-Einstein principle says that each photon of light absorbed by chemical system, only one molecule could be activated. And here Einstein's equivalency principle says that the opposite, one particle of a chemical substance can absorb only one photon, whereas Stark-Einstein's law states that one photon can activate only one molecule. Please understand. And what are the utilities of this laws if you ask? Calculation of the rates of the formation of the reactive intermediate in photochemical reactions and the study of the mechanism of the photochemical reactions. Luminescence. What is this luminescence? Luminescence means the glow produced in the body by method other than the action of heat. So all visible glow, according to our experience, is something related to heat. Whereas here, there is a possibility of the glow which is not by the action of heat. The production of the cold light is called luminescence. Luminescence means light is produced other than the means of heat. So let's see what are they. First one is chemiluminescence. The emission of light in the chemical reaction at ordinary temperature is called chemiluminescence. Example, light emitted by glowworms, like we say minna minunga. Best example is fluorescence. Certain substances, when exposed to light or certain other radiations, absorb energy and then immediately start re-emitting the energy, re-emitting the energy. Such as substances are called fluorescent substances, and the phenomenon is called fluorescence. Organic dyes such as eosine, fluorescein, etc., vapor of sodium, mercury, iodine, etc. The other luminescence, chemiluminescence, is phosphorescence, where there are certain substances which continue to glow for some more time even after the external light is cut off. Thus the phosphorescence is a slow process comparing to fluorescence, or it could be told as slow fluorescence.